Actually, I listened to a couple of talks before here, and I realized that my talk will be drastically different from the other talks. I don't do cryptography, first of all. Second, you won't see any Greek characters in my slides, and almost no equations. But I do, what I do is I do computer science. I do networking and operating system. I do actually build systems using cryptographic operations. And today I'm going to talk a little bit about how we improve the performance of cryptographic operations on like modern general purpose processors. So this might give you a sense of a practical cryptography that's being used right now. So I know that you're studying post-quantum cryptography. I hope that will replace the current system. Then you might want to have a sense of performance that's being expected actually in the industry these days. So for 40 years of internet history, actually the internet traffic is still rapidly increasing. So Cisco predicts that the internet traffic is increasing 22% by year. And then at the end of 2020, we'll see about 194 exabytes per month of internet uses per month. And what's good news for cryptographers is that the encrypted traffic actually is growing fast too. So last year, we see about 57% of all internet traffic is being encrypted. So the fast cryptographic operation is very important. And not, yes, the green is total number of bytes, and then the blue lines it shows only web transactions. So there are web transactions, there are P2P traffic, there are video traffics that are not based on web. So the total number is actually larger.
More than a half of all the transactions
Yes.
over the internet are included.
Yes, already.
Cannot believe it.
And actually, if you look at the cellular traffic side, so we use a lot of private information. And we expect actually over 60% of all traffic is already encrypted. We're using HTTPS like unknowingly actually. And then we don't actually see much performance problem these days, right?
I don't get the second part. You mean that out of these 57% of the traffic, 32% is coming from Cisco.
Yes, yes.
So the rest is coming from
What they are delivering the traffic using the protocol, not HTTP. So they like video using non-HTTP. There are HTTP-based video delivery, but there are also not. There are traffic based on non-HTTP protocols too. So there might be more traffic out of the non-HTTP, but that takes up more number of bytes actually. So not surprisingly, we're seeing more and more HTTPS sites. This shows the growing number of SSL certificates. So we actually see about 1,000 times increase in the number of valid SSL TLS certificates for the past 18 years. So here is the November 1996, and that's number one. And then November 2014, we see about 1,000 times more certificates. So more and more internet sites are becoming providing SSL. And then actually, about 5 years ago, Facebook didn't support SSL. And Facebook, even Google, didn't support SSL in 2008. 2009, they started to support SSL in Gmail, right? But these days, most popular sites actually support SSL. Google, Facebook, Amazon, Twitter, almost all like important sites actually support encrypted data traffic. YouTube actually support it. YouTube support HTTPS by default in the US. I'm not sure about here, but actually you can choose to use HTTPS, and you won't see much performance difference actually. Yeah. So it's getting important. So in my talk, I'll talk a little bit about the practical side of cryptography. So as an administrator of a website, we want to provide high quality traffic encryption at a small cost. By high quality, we mean we want to provide use secure protocols and implementations, and that we need to do also the secure key management. So that's kind of an assumption here. But with that in mind, we want to improve the performance with modern processors. So we see actually a lot of CPUs and that are low cost and that actually had, so these days CPUs have multiple cores. So like some of the servers have like 14 cores to like 28 cores in one CPU. But there's another type of a processor called GPU, and that has like 1,000 cores in there. So using these cores, using these processors, you might want to provide cost-effective crypto performance accelerations at low cost. And the key actually here is that the exploiting the parallelism in doing the operations. So I'll show how you do that in one of the some of the examples. So I mainly talk about SSL and IPsec performance because they are most widely used in virtual private network and secure web transactions like TLS or HTTPS transactions. And I'll talk mainly about my work, SSL Traders. It's published 5 years ago, and my recent work on APU, which the APU is a kind of process that has both CPU and GPU in one chip. So you can use both processors in one chip using sharing the same RAM. Okay, let me talk a little bit about SSL. So secure sockets layer or transport TLS, transport layer security, same thing actually. So this is a de facto standard protocol for secure network communication. So basically provides three properties: authentication, confidentiality, and content integrity. So this is roughly how it works. Conceptually, it's very simple. Client and server make a connection. Typically, they make a TCP connection. And then they agree on keys using one of the public key cryptography, like RSA and Diffie-Hellman. And then if they agree on the keys, then all the data now is encrypted. And using using SHA-1 or some functionality hash function, you can actually provide the content integrity as well. But if you want to use SSL in real world, you have to pay the price. So by the overhead, HTTPS actually consumes about 22 times more computation cycles for connection setup. Connection setup means that you're doing key agreement, like SSL handshake. Okay. And you have to spend about 50 times more computation cycles for data transfer for encryption. So if you want good privacy, maybe you need more money. Okay, so you can buy more machines. Okay, or you can adopt some of the hardware SSL accelerators. They're kind of expensive. And then if you're thinking about more servers, right? So Google, Facebook has 1.6 billion users. And how many servers you need to buy, right? So if you can make the throughput, if you can improve the throughput a little bit, then you can save a lot of money actually here. So as one solution, actually we suggest to think about GPU to offload some of the SSL operations. So I'll talk a little bit about the GPU. So GPU stands for graphics processing unit. It's a requirement for 3D gaming actually. So it's the main chip of the graphics card, and it's mainly used for real-time 3D game rendering. So it has massively parallel processing capacity. So using the GPU, you can independently calculate the intensity of each pixel in parallel. So that's where you get the parallel computation power. Okay. If you compare CPU versus GPU, CPU has small number of cores, but each individual core is really, really fast and really, really smart. But if you think about GPU, you have a large number of cores, but each core is kind of wimpy. It's not very smart, but you have a large number of them. Okay. If you look at the die space, then so here is one top-of-the-line CPU, Intel Xeon E5-2697 version 3, which has 14 cores, and it has very sophisticated logic for control and cache, L1, L2, L3 cache, and then it has small number of ALU units, arithmetic logic units. They're basically used for computation, right? But if you look at GPU, so NVIDIA Titan X is one of the recent GPU. It spends majority of its die space on calculation, ALU. Okay, it has 1,072 cores. So if you look at the raw performance, actually, GPU has about 20 times more computation power than CPU. And actually, if you look at the price of this CPU, it's about $2,100, and this one is about $1,200. It's about half the price. So actually, effectively, you get about 40 times performance improvement, like computation power in GPU. So GPU adopts a different execution model called single instruction multiple threads. So let me show you some example here. Let's say you want to add two vectors, one-dimensional vectors array. And then if you write the code in C, it looks like this. You have just one loop, iterate from 0 to n minus 1, and then you just update, right? But the way you write the code in GPU is different. You write one addition per specific index. So you write this code for a specific index, and then you execute n threads, n parallel threads at the same time, right? So this one addition is run in parallel. Okay, so you get the parallel power because you have large number of small cores. Okay, so that's how you write the code in GPU. So in summary, the benefits of GPU over CPU is summarized as this. The GPU generally has a higher raw computation power. So the comparison is the same here. A typical GPU has about 20 times more computation power. And then second point is that GPU has the ability to hide memory access. So when you try to do some operation, you read some variable from memory, and it takes about 100 cycles. During that time, you cannot do anything because you have to get the memory, the value on this the register to do the operation. But in GPU, when you're stalling due to the memory access, then that thread is automatically switched to another thread that can do computation. That's done by hardware. So you can actually overlap memory access latency with actually other computations. So that's actually built into GPU. It's very good, actually. Another benefit of GPU is GPU has about 5 times more memory bandwidth. So if you're doing lots of computation intensive or memory intensive operations, GPU might help a lot. Okay? But then you might think that why not just use GPU everywhere? Why? If GPU is good, then do not use CPU, right? No, you can't do that. The big caveat is that 1, 2, 3, these are realizable only when there is lots of parallelism. If you're writing the code that's serial, like so you have write one instructions and the next instruction is depending on the result of the previous instruction, right? If you have dependency, then you cannot parallelize it, right? Then CPU is way faster than GPU. So there's no free lunch. Do you have any question?
So the first one, you compared one CPU and one GPU.
Yes. So one CPU has 14 cores, 14 processors, and Titan X has 3,000 cores at the half price. Yeah.
With many cores.
Yes. So each small core is very wimpy. It's not that good. But if you have a lot of them, and if you benefit from parallelism, you get a lot of performance actually. Okay.
They're also common.
Yes, 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 yes. So so if you get the maximum performance out of GPU, you want some independent jobs run in parallel, and then each independent job should not have some many branches, right? Depending on this, and then some thread has to go this way, some thread has to go that way. So then everything is serialized, and the performance is very bad. So if everyone goes the same direction, then you get the best performance. But if you look at the like AES or SHA-1, you don't have much branches actually. So you don't have to worry too much about that. So using GPU, actually built a system called SSL Shader, which is a SSL reverse proxy. So the clients and proxy is talking to each other with SSL. And then SSL Shader decrypts the data and then talk to the backend server in plain text TCP. We assume that this area is safe, or you can use some symmetric cryptography, like cheap cryptography operations there. Uh, then then the benefit of the SSL reverse proxy is that you don't have to modify the existing backend servers. So in order to support SSL TLS, you only put this guy, and then all these guys talking to this guy, and then that traffic is unencrypted to a web server, and they get it back, and then encrypt again and send it back to the client. Okay, so this is actually widely popular model in middle box. You can actually buy some middle boxes like this. So in order to use the parallelism, so you need to find some parallelism in SSL processing. There are basically three points, three places where you can find some parallelism. So SSL Shader is talking to a lot of independent clients. So you may find some parallelism among independent sessions. But even inside one session, you're dealing with multiple SSL records. So you gather some of the records in batch and then run it at the same time. Or inside one cryptographic operation, you may be able to find some parallelism too. So for implementation, actually, we choose one widely used cipher suite. We use RSA, very pre-quantum cryptography, sorry, but it's very widely used. And then we use AES and SHA-1 for symmetric encryption and content integrity. And we do optimize of GPU algorithms by using by exploiting massive parallel processing. So we try to show one parallelization algorithm first, and then talk about the batch processing. So RSA, again, let's say you have M as plain text, and C is a ciphertext. EN is public key, DN is private key. And the beauty of RSA is the encryption and decryption is the same. The algorithm is the same. You have M to the power of E modulo N that becomes ciphertext, and then you do ciphertext to the power of D modulo N that becomes M. So which one is more expensive, encryption or decryption? Question. Yes, decryption is more expensive. Why? Because E is small. So for encryption, you use actually small exponent, 3, 17, yeah, 2 to the n plus 1, yeah, 65537. But for decryption, D is either like 1024 bits. 1024 bits is not secure these days. 2048 bits or 4096 bits are used, but 4K is not really used due to the performance problem. So 2K key is actually widely used. And in terms of digits, it's about 300 to 600 digits. So not surprisingly, decryption is the bottleneck, but decryption has to be done in the server side. So some people say that's wrong, because you have lots of client, and if you can do the decryption at the client side, then you may be able to offload a lot of computation cycles from server, because server has to deal with lots of clients, right? But current TLS, current SSL requires the server to decrypt the key. Okay, so decryption is the bottleneck, and the server side is the bottleneck.
So when you download some files from
Yes.
server, in
Yeah.
that case, the server encrypts and then
Yes. Yes. Yeah. Yeah. So that's symmetric. So you spend actually same amount of time, same amount of operations actually on symmetric key encryption decryption. I think it roughly takes up a similar amount of computation. But RSA, public key cryptography, decryption spends a lot more, like 20 to 60 times more computation cycles, and then server becomes the bottleneck. So it depends on how big the content is. If the content is small, then SSL handshake, the key agreement, becomes the bottleneck. If content is large, then symmetric cipher becomes the bottleneck.
yeah,
Okay.
then it's in the SSL protocol, the protocol is handshake protocol is asymmetric. Then the
Yes.
client encrypt the key.
Yes. Yeah. Client generates key and then give it to server, and server decrypts the key. Okay. Yeah. Roughly. Yeah. So, but if you look at the modular exponentiation, it looks to be lots of multiplications. So if you do something about multiplications, then we may be able to improve performance. So let's look at how we do multiplication in school. 649 times 627. Okay. So if you look at all this, then the multiplication itself, right, is independent. So that can be parallelized. Problem is that you need to add them all, and then while you're adding, you produce carries. Carry propagates. Carry is dependency, so it's difficult to parallelize because of the carry. So we actually came up with one algorithm to do it better. So let's say you have two integers, large integers, and then that consists of s words, right? S, maybe you can think of it as words is one digit, but typically in one word is 64-bit. So in actual implementation, large number is represented as an array of words, okay? And then words is typically 64-bit. And then so if you're using 2048-bit key, right, number, that's about 32 words, right? If you use a 64-bit word. So forget about the word. I mean, just the word as one word is one digit. Okay, let's do same calculation. 649, times 627. Then you do the multiplication in parallel, and then when you write the result, you separate the higher word part here. So let's say 79. That's 63. So you write 6 here and 3 in the low part there. Okay, you separate these two word in different positions. Okay, so for example, 7 times 40 is 28, right? 7 4 is 28. 2, write 2 here and 8 there. Right? If you write all that like that, then you have 7 rows, right? And then this guy's 283 is in the position of 1. And then 288 actually is in the position of 10. It's a 2,880. Okay? 64400, something like that. And then here 4260, right? 10100, something like that. And then you add them all here. So 283 is added. And then you need to add 28802 here. And each addition also needs to be parallel. So you can add the two words in the same position. And if you have a carry, then don't propagate it. Just remember here. Write it here. Write it here. So 2883 is here, and 2880, then you add them in parallel. And if you have carry, you temporarily write the carry here. And then you go on. Maybe so you have 6 times to do the addition, right? And then carry is just added to here temporarily. Then when you're all done, then you add this guy and this guy in parallel too. And if that generates a carry, you write it here again. And you do this operation until there's no carry. Then in the worst case, you can compute s minus 1 times for carry processing. But in reality, it requires about 1 or 2 steps in most times. So mostly, it takes up about 2s steps, which is OS. So you can calculate the multiplication in OS step. And the previous well-known, the fastest algorithm was using S log S. And it looks to be similar, S versus S log S, but if S is large, then you deal with a lot of numbers, the performance improvement actually a lot. Any question? Okay, let's move on. So this is not the only algorithm that we use. We use the standard optimization for RSA, Chinese remainder theorem, Montgomery multiplication, etc. And then we also try to parallelize lots of serial algorithms and then use some GPU-specific optimizations as well. So by using all of this, actually, we could improve the RSA performance a lot. And then using one GPU, you could do about more than 70,000 decryptions per second. So this is using 1024-bit, so it's slightly older, but still, it's pretty good. So if you if you want to know details about this, then you may want to read our earlier paper. So now we're done with exploiting parallelism in cryptographic operations. Now we move on to exploiting the multiple sessions, and then in order to get the parallelism, actually we need to do some batch processing. So before going there, we actually measured the performance of GPU using individual cryptographic primitive, and then we compare the performance against one CPU core. So this is 5 years ago. And then if you do the operation one at a time, no parallelism, then the performance is a lot worse than the one CPU core. Only 8% you can get the performance. If you do AES decryption, so we actually use the CBC mode. If you use AES decryption, then you get a little bit of parallelism in decryption, but yeah, you can't do that in encryption. So that's why the encryption performance is much lower, but decryption is slightly better. But it's not a lot better than CPU core. But if you process multiple methods at one time, okay, not one at a time, right? Then you actually get a lot of performance improvement due to utilization of parallel cores in GPU, because you have thousands of cores, and then you can utilize more GPU cores to get the performance. And RSA actually shows about 22 times better performance than a single CPU core. Okay, and then AES and then SHA-1 shows a little bit lower than RSA, but it shows significantly better than the previous slide. Why do we actually see lower performance improvement here? That is related to the computation, the copy overhead. So in order to use GPU, you actually need to copy the data from CPU RAM to GPU RAM using PCI Express I/O bus, and that takes up time. So let me show how GPU kernel works here. So the copy overhead is actually a big overhead in GPU computation. So when you use GPU, first thing you need to do is you need to copy the data to be encrypted, right? From CPU memory to GPU memory, and then do the computation. And then copy the result back from the GPU memory to CPU memory. So If you do not copy, actually, then so let's assume that you only measured the performance of this guy, and then you get about 2 times to 4 times better performance than doing all of this. So using PCI Express, another way of saying is that using PCI Express actually uh, degrades the performance by a factor of 4, right?
I don't get what is mean copy or without copy.
Oh,
You
with
still have to transfer.
so with copy means you do all this, all three. Okay. Without copy means you skip these two things. So you just measured only this guy because this guy is important, right? But if you actually in the real world, computation is important, but the I/O is also important. It looks to be more important. 4 times you spend.
So if you come back to the previous slide, the one
Sure.
that had RSA, the reason why you get more with RSA, just because in RSA you encrypt all messages. So I mean, yes, you have to access all these and all.
Actually, it's not like it's not just copy. Yes, the algorithm itself is different, right? AES and then RSA algorithm itself is different. So yes, but uh, one factor is copying overhead. But if you remove the copy overhead, then can you say that it's the same as RSA? We cannot say that because algorithm itself is different. So RSA is actually a computation intensive. You do a lot of computation. AES and SHA-1 actually is doing lots of memory read, kind of streaming. You don't do a lot of computation. You do shifts and do lots of things, other things, but not like multiplication a lot. So you cannot really compare where the performance difference comes from. But one clear factor here is that the copying overhead actually dominates, I mean, reduces the performance of AES and SHA-1. Because here, RSA, as you say, is encrypting or decrypting small message, right? But this guy has to encrypt the entire content, right? So it has to copy a lot more data between the CPU and GPU, right?
So then you have a mixed operation, parallel operation and the non-parallel operation. Then
Right.
you do all the things in GPU or you compute in GPU and CPU.
Good question. So in order to get the best performance out of CPU and GPU combined, if you may want to run serial operations in CPU and then all parallel operations in GPU. If there is some serial operation in GPU, that drastically degrades performance of the entire GPU performance, actually.
Then means that in that case I can get in AES that some parts are parallelizable but
Yeah.
some parts are not.
Yeah.
So you should switch CPU and GPU repeatedly.
Actually, CPU and GPU can run in parallel. So you don't have to wait until GPU is running or finished, right? So CPU can accept another connections while GPU is calculating RSA. So you can do that same. You can overlap these computations between CPU and GPU. Yes, because you know when the GPU finishes. So yeah, that synchronization is the low overhead. Okay. So let's move on. So how do you improve the situation here? We can use pipelining. So without pipelining, so what you need to do is you need to copy the data from CPU and GPU, and then you do execution, and then you need to copy the result back. So let's say all this stage takes just 1T, then it'll take 3T latency. But simple idea is that while you're when you move the data to here while the GPU is running, you may copy the next batch at the same time. So you can actually overlap the copying and execution at the same time. It's called concurrent copy and execution, and it improves a little bit of performance, about 36% to 51%, not much. But still, if you do that, then we have like 9 times better performance than one single core, and 14 times better performance than single CPU core. Okay. So in summary, GPU performance as fast as 9 to 28 CPU cores. And the RSA, this is a slightly old, 1024. We could do about 90,000 decryptions per second. And then SHA-1, we could do 47 gigabits per second, while CPU core can do only 3,000 at that time. So the lessons here is that batch processing is very essential to fully utilize GPU. And AES and SHA-1, they are bottlenecked at data copy. Actually, before, while preparing this talk, actually, I measured the performance with more recent processors. And so E5 2697 is one of the top of the line CPU. And we use 2048 bit. And then if you use Titan X, actually, you get about 2.2 times better performance than entire CPU, or 31 times better performance than CPU cores. Okay, so it's like you have 31 CPU cores in GPU. That's performance you can get. A similar trend if you increase the key size to 4K, actually. But then the performance-wise, the price-wise, E5 is about $2,100, and then Titan X is about $1,200. So the performance per cost per dollar is actually larger than 2 times. It's maybe 4 times. Okay, it's very cost-effective to use the GPU for cryptographic operations at least. And then HMAX SHA-1, similar trend. We see about 2 times performance improvement for entire CPU. But if you look at AES, then you see this CPU is better in terms of performance. Do you see why? Huh? You cannot parallelize rounds. Yeah. Actually, the real answer is that the Intel and AMD implemented AES in hardware. So they have a specialized hardware instructions, really, really fast. No GPU can beat that. But they cannot. I'm not sure if they have a plan to implement RSA in hardware. Not sure, but maybe. But so at least AES, I think you can benefit from CPU these days, actually. The NTU. Okay. About RSA or yeah. So they have some instructions to do the multiplication of large numbers, but I think it's about last time I heard is it was about 512 bits. Okay, so maybe you're closer to 2K, but I don't know yet. So let's move on to actually building the proxy itself. So then how do you utilize GPU? How do you get the parallelism in GPU? So one idea is you get lots of data from the clients and then batch them all and then give the workload to GPU at once. But waiting for fixed batch size actually doesn't work because the network traffic is varying over time, right? In late night, you have a lot of traffic. In the early morning, you don't really have traffic, right? You don't have to, if you wait for fixed batch size, then it'll increase latency, right? So we have the batch size to be dynamically adjusted to the queue length. And for small batch also, maybe CPUs are faster. So if you do if you encrypt one message at a time, then CPUs are much faster than GPU. So to exploit that, if the load is small, workload is small, then maybe you can use a CPU instead of using GPU. And that only when the input queue length is larger than some threshold, then you offload the cryptographic operations to GPU. So we call that opportunistic offloading. And then if you have multiple cores, then each cores collect the input, and then you increase the batch size actually, and then you keep the workload to the single GPU queue to improve the parallelism on GPU. So per each core, you have a worker thread, and then it's doing network session handling, and cryptographic operations, but you actually share one CPU across multiple cores so that you get more workload piled up to be sent to GPU to utilize GPU more. Okay. And actually, we measure the performance of web transactions. So HTTPS connection rate. So we use modern size RSA 2048 and AES 128 bits and HMAC SHA-1 is cipher suite. And then we're just downloading 1 byte at a time and then disconnect. Okay, and then we measured how many transactions you can do per second. And we use E5 2797 97 CPU, and then possibly one GPU. So this guy is using only CPU, and this guy is using this guy and this GPU. So if you use more GPU, better GPU, then actually you see performance improvement. And if you use Titan X, actually you have 6.2 times more transactions per second than using only CPU. Okay. So about the performance, it's about 28,000 transactions per second. So if you actually the F5 and Citrix, the companies, they sell SSL proxy, and I mean, if you pay more, you get better performance. But 20K RSA performance is pretty good actually. You have to pay at least $80,000 to buy that, but this one is only $12,000. So you can with GPU you can improve performance in cost effectively. That's the point here. And then we also show some of the measurements done 5 years ago. But the performance trend is actually very similar to recent processors. We use 1024 RSA bit, the key size of RSA, and 128-bit AES and HMAC SHA-1 same, 2 CPU and 2 kind of old GPU, and 10G network card. And the comparison here is that we have proxy and web server, plain text web server, versus the web server itself supports SSL. So we compare these two. And when 1,000 connections are made concurrently, then this shows the latency of one byte HTTP object fetch. Okay. Then it shows the CDF, and the x-axis shows the latency. And SSH header is slower than just plain light HTTP, but the difference is about 1 millisecond. Okay. And then actually light HTTP has a longer tail. Right, so the slower one is even more slower than SSH header client. But when there is a heavy load, like 30,000 concurrent connections, then SSH header shows much better performance, much lower latency, and then than the light HTTP. So SSH header can do about 29,000 connections per second, while light HTTPD can do only about 11,000 connections per second. So it's just slower, but the latency is also larger than SSH header. What about the data transfer performance? So this is a light HTTPD performance as just one. And then if you use small content size, actually you benefit from the performance improvement of RSA. So you get higher performance. But if you use large content, then the performance dominates. Performance actually is dominated by the AES, and that's benefiting from the CPU. And then if you use proxy and light HTTP, right? So we use proxy and web server, then there has to be copy between these two servers. So there's extra overhead in our case. So that's why it's lower than the just light HTTP itself. But still, we see about 13 kilobits per second. Okay, and then most web content size is actually smaller than 100K. So you get actually benefit from using GPU. So recently, we do actually work on APU. So as I said earlier, APU is accelerated processing unit. Basically, CPU and GPU is in this one chip. So if you buy the chip, then CPU, so there is CPU part, and then there is GPU part in the one chip. Strength is that so you don't have to use PCI Express to share the content because they share the same memory. Okay, and then low power consumption. They're using about 35 watts, and it's about 25% of the typical CPU. And inexpensive. It's about $150. It's very inexpensive. And then weakness is that they share the memory bandwidth, so there might be contention between the CPU and GPU. If CPU is running, CPU and GPU are running at the same time at full speed, the memory becomes the bottleneck. Okay? So actually measure the performance of IPsec gateway used on this machine. And we still see, so this is the packet size and then the throughput. And if you look at the largest packet size, this is this guy is CPU baseline, and then there is some CPU optimizations here. So even if you do CPU optimization, performance improvement is small. But if you use GPU at the same time, then you get about 2.2 times performance improvement over CPU only approach. Another way of saying it is that we see about 16 gigabits per second for machine priced $1,000 or lower. So you can so this is a practical performance we can see actually in industry in the world actually. So conclusion, GPU is very beneficial to compute intensive operations, network operations applications like cryptographic operations. So we actually did this RSA implementation, and the performance is actually the best, what's best. We do about 29,000 transactions per second with RSA 2048 bit. It's comparable to like 30 CPU cores, or it's similar to actually high-end hardware accelerators. These guys can do between 20K to like 80K. 80K is very expensive. And SSL shader can do transparent integration, and then we can effectively utilize GPU for SSL processing. And up to, we show improved performance, connection performance by up to 6 times, or we can achieve 13 gigabits per second on relatively old machine actually. So and then the bottleneck actually is not in GPU here. Actually, the bottleneck was in the TCP stack itself. So actually, if you use a better TCP stack, then you can actually even improve the performance. And then here, the overhead is actually copied. So if you are interested, you can actually look at the website of our SSL shader. Okay, so if you have any questions, please feel free.
Any question? Yes.
How easy is it to program a GPU now? So for the programming, how is it easy or difficult now?
It takes some time because so you use C. So that's, I mean, if you're familiar with C language, then you can use C. But the way GPU works is different from the way CPU works. As I said earlier, it's using single instruction, multiple threads. So there are multiple threads that are sharing the same instructions. And then if they are fetching different data and then move along together, then you get the best performance. But if these threads are doing different things, then you have to wait until others finish. So that's all serialized. Then performance is really bad. But programming itself, right? The programming itself is easy. You can write just the program in C. But in order to get the best performance, good performance, you need to be careful about how you program. Yeah. But it takes about like two months to realize that. So it was not too bad actually.
Any other question? So I just have a simple question to ask you then. So Intel now putting those SSE commands inside.
SSE.
Yes, this is a vector instruction
Yeah.
operations. And if you do those things, can the performance be improved? I mean,
Yes.
very similar?
If you can utilize vector instruction, you can do that. You can improve performance a little bit. But you can see the GPU is kind of generalization of the SSE. You have more SSE in the GPU, and the more benefit from GPU. So SSE, so you get benefit from SSE, but the performance improvement is kind of limited in CPU, right? Because CPU has to do other things too, but because GPU has lots of cores that are dedicated to do kind of SSE, the single instruction multiple thread. So if you do a lot of parallel operations, then you may benefit from GPU more actually.
And
How about floating point arithmetic? Can you do?
I'm sorry?
Before a few years ago, there was a problem with floating point arithmetic on GPU. Floating point.
I don't think we have floating point problems these days. Yeah, I understand there was a problem, but I don't do floating point operations here. I do mostly integer operations, but I think it went away, I think. There was a like error, I think, when you do a lot of floating point operations in GPU, but I think they somehow fixed it. I don't know how, but yeah. I could be wrong, so yeah.
any other question? So if not, let's thank the speaker again.
Thank you.